Welcome everyone. We are here on lecture 5 and we are currently talking about unit 4 of the course, which deals with regular expressions. We are still reading Sipser book and we are still at chapter 1. Today we will be talking about regular expressions and equivalence of regular expressions and regular languages. I would like to remind you that you probably used regular expressions as validation functions for programming languages. You used regular expressions in Java. You have a validator, a regular expression in several internet programming languages. So regular expressions can be used in different topics like compilation, and understanding of natural languages and translation, automatic translation or robotic translation of the languages. So it's a fascinating topic and I would like you to understand it, and I think it's a relatively simple topic. Okay, let's start with comparison of regular expressions and the algebraic expressions that we use. Okay, irregular languages can be described with regular expressions. Like in arithmetics, when I write some arithmetic expression with numbers and operations, for example, like 2 plus 3 multiply 5, I'm using some algebraic notation that I can easily understand. I understand that 2 plus 3 I do as the first operation, then I multiply it by 5, and the result is the number 25. The result of a regular expression that we will write won't be a number. The result of regular expression will be a set of words, or it can be defined as a regular language. So the value of regular expression is a regular language. The notation and the operations that we will use, the regular operation we can use are or, and we will use plus notation. Additional operation will be clean star, and we can use a star operation. And additional operation can be concatenation, and we can use R concatenation S, but usually we just write RS without any dot notation in between. So let's say on an example here, I am giving a language 0 or 1 and star operation on 0 on 1 concatenation with 0. So I'm talking about all the words ending with 0, basically, over alphabet 0, 1. I would like to give a formal definition of a set of regular expression. A set of regular expressions over an alphabet sigma is defined inductively as follows. An empty word is regular expression. An empty set is regular expression. A single letter is regular expression. It is the basis of induction. And now our induction. If R and S are regular expression, then R in brackets is a regular expression. R plus S is a regular expression. R concatenation S is a regular expression. And R star is a regular expression. Let's see some examples over alphabet AB. Epsilon is a regular expression, A is a regular expression, A or B is a regular expression, B star is a regular expression. A or B concatenation, B is regular expression. A concatenation, B star is regular expression. A, B parenthesis star is regular expression, and so on. I would like to remind you the priority of regular operations. So if you have an expression with brackets, with plus, with star operation, what do you do first? So basically you start with brackets. Then you move to star operation. Then you move to concatenation, and the last operation is plus, which means or. So basically, when I have B or A, B star, first of all, I compute B star, then I concatenate A with B star, and then I can choose between B or A, B star. Some common notations that we use are concatenation S. We usually write RS without any dot or that means concatenation. We just omit it. R in power of plus means R concatenation with R star. And sometimes we write alphabet sigma as sigma 1 plus sigma 2 plus sigma 3. We use letters of sigma 1 and we choose a single letter from large sigma notation. Let's talk about regular expressions and regular languages. Let's say that we have some regular expression R and we have a language of regular expression R, LR. And we have the following definition. L of regular expression empty set is an empty set. L of regular expression epsilon is a language with epsilon word. L of regular expression sigma is the language with sigma, and it can be defined for any letter of the alphabet. Language of regular expression R or S is the language of regular expression R union with the language of regular expression S. Language of regular expression R concatenation S is the language of R concatenation with the language of S. And language of R star is the language of R that we use a star operation on the language of R. So we use concatenation from 0 till infinity as much as we like to concatenate LR with itself. Okay, let's see some examples of languages, and we will do first 3 examples during the lecture, and the rest we will do during our practice exercises. We are given alphabet 0, 1, and you are asked to describe each language as a regular expression. The first language, L1, W such that W has a single 1. L2, W has at least one 1. L3, W contains the string 110. L4, W such that the length of W modulo 2 equals 0. L5, W such that W starts with 1. L6, W that W ends with 0, 0. And once again, I will start with first 3 languages, and the rest we will do during the practical exercises. Okay, so let's do our first 3 questions. I advise you to stop the lecture, try to solve these questions by yourself, and then to check the solution with the class solution. The first language, L1, all the words W such that W has a single 1. I can rewrite L1 in the following form. W belongs to alphabet 0, 1 star. DS1 on W equals 1. The number of ones in W equals 1. And now finally the regular expression R1. I'm using the single 1 and some prefix before and some suffix after. The prefix and suffix I want to have only zeros since I can use the single 1. So I write 0 star 1 0 star. So I'm using only 1 1 and I can have some prefix of zeros before and some suffix of zeros after. Okay, the next language, L2. Words W such that W has at least one. So here we have a little bit different definition. Once again, I can give the formal description of the language a little bit differently, not in words but in signs. I can define L2 W such that DS1W greater equals to 1. The number of ones in W greater equals to 1. That means at least one. And now I can write the regular expression. Once again, I have one in the middle, and I have some prefix and suffix before, but now in prefix and suffix, I allowed to use zeros and ones. So I have some prefix of 0 and 1 plus 0 star. Then I have at least one, and then I have suffix 1 or 0 star. This regular expression can be rewritten as sigma star 1 sigma star. And now we know that we have at least one, but we can have more ones. Okay, the next language, L3, the last for classroom. The rest we will continue during the practical exercises. Okay, L3, W. W contains the string 110. So basically, I would like a regular expression that has 110 and some prefix and some suffix. So the formal definition, I can't write the better formal definition, or let's say that the best formal definition is regular expressions that I used. R3, we have some prefix, sigma star, 110, the substring that we were asked to use, and sigma star once again as a suffix. So we definitely have substring 110 with some prefix and some suffix before and after. Additional languages that we will be using during our practical exercises, languages L7 till L13. Once again, we will have to write maybe better formal description of the language, and we will have to write a regular expression for those languages. Since regular expressions are, let's say, equivalent to algebraic expressions, we can have also some properties of regular expressions here. Useful properties of regular expressions are mentioned here. ROS equals to S or R. It doesn't matter what I choose, R or S, so we can write ROS or S plus R, it doesn't matter. R plus an empty set equals to empty set plus R and equals to R itself. Empty set or something, we choose something. R plus R, the meaning is R. If you choose R or R, additional R doesn't help you. We have a single R. Concatenation with an empty set equals to an empty set. R concatenation with phi equals to phi concatenation with R and equals to an empty set. R concatenation with R start can be rewritten as R plus the positive closure operation. But please pay attention that you write this plus in power, not a plus between R and R. Otherwise, it's a definition of OR sign. R concatenation with an empty word equals to an empty word concatenation with R and equals to R itself. We continue. Additional properties of regular expressions are R concatenation with SOT equals RS or RT. You can do concatenation of R with S or concatenation of R with T. R or brackets S or T can be rewritten as R or S as the first operation and plus t is the second operation. The same with concatenation. R concatenation with brackets S concatenation with t can be rewritten or used as R concatenation with S at the beginning and then concatenation with t. R star can be rewritten as R star in brackets in power of star. It doesn't matter how many times I apply star with itself. It's infinite operation, so nothing changes. It can be rewritten as R star concatenation with R star, since we anyway use concatenation size. It can be rewritten as R star plus R. Additional property, R star or R plus. Please pay attention that we will choose R star. Since in R plus we have all the same expression, but we don't have an empty word. So R star is a larger set, usually is a larger set, not definitely. So we will choose R star as a resulting set. Equivalence of regular expressions. To prove that two regular expressions R and S are equivalent, you need to show that the languages of R is subset of the language of S and the language of S is subset of the language of R. To show that two regular expressions are not equivalent is much easier. You just have to find one word that will be accepted by one regular expression and will be rejected by another one. And this way you prove that two regular expressions are not equivalent. Let's see some examples and let's do some proofs. We are given a regular expression R, which is epsilon or 0 or plus 1 star, a concatenation with 1. And we are giving a regular expression S, 0 star 1, brackets, star. The question is, are R and S equivalent? And they are equivalent, and we will prove it by bidirectional inclusion. We will prove that LS is a subset of LR and LR is a subset of LS. So let's start the formal proof. The first direction we will prove, we will take the word W that belongs to LS and we will prove that it also belongs to LR. Okay, we will start with the word W that belongs to 0 star 1 brackets star. As a word W can be of, we can have two possibilities of the word W. We can have an empty word if we use star operation 0 times, or we can have some word that is concatenation of x1, x2, xn, where each xi belongs to 0 star 1, and we used the star operation n times here, and n can be greater than 0. If W is an empty word, then W belongs to R, since we have epsilon or. So we know that W that is epsilon definitely belongs to R. Let's see the second part. W is divided to x1, x2, xn, and it can be rewritten as W cap 1. I can look at n minus 1 sub-expressions without definite number of zeros or 1. And I will look at the last substring xn, and I will divide it to some number of zeros and additional 1. And let's say that the number of zeros can be greater equal to 0. It doesn't matter from our point of view. But if the word W can be rewritten in this way, it means that W tag belongs to 0 or 1 star, because I don't know what is x1, x2, xn minus 1, but I know that there are words over alphabet 0, 1. So I can definitely claim that W cap is the word that belongs to 0 or 1 star. So I can look at W cap with concatenation 1, and I can claim that W can 1 belongs to the language 0 or 1 star concatenation with 1, which is LR. So I took the word W that belonged to regular expression S, and I proved that all the possibilities of W also belong to R. The second direction. We will take a word W that belongs to R, which is epsilon or 0 or 1 star concatenation with 1. And we will prove that the word W also belongs to S. Once again, we will divide W on an empty word, okay? And an empty word belongs to LS. Since I can use concatenation, I can use star operation 0 times and not to concatenate the language with itself. And we will have an empty string as a result. And I can take W as not an empty word, and it is some prefix of 0 and 1s, and then the suffix of the single one. I will rewrite W in the following way. I will rewrite a word W as W cap with concatenation with 1. And then I will check how many ones I have in W cap. And let's say that I have K ones in WK. So I will rewrite W cap as K substrings. X1 concatenation with 1, X2 concatenation with 1, X3 concatenation with 1, XK concatenation with 1, and XK plus 1, where each X is actually some sequence of 0. So Xi belongs to 0 star. But if W cap can be rewritten in this way, I can claim that the original word W, which is W cap concatenation with 1, can be rewritten as set of zeros 1, concatenation set of zeros 1, concatenation set of zeros 1, and I can do it K plus 1 times. And the meaning of what is written here, that W belongs to 0 star 1 brackets star. The W belongs to the regular expression 0 star 1 brackets star. Let's move to another example. We have two regular expressions, R and S, and once again we are asked, do we have the same expression or the same language or not the same language? R, and S equivalent. And in this example, the answer is no. The answer no is much simpler to prove. I just have to find one word that belongs to first expression and doesn't belong to the second expression. So the expression R is 0 or 1 star concatenation with 1 or 0 star. The second one, 0 or 1 concatenation with 0 star 1 brackets star. So let's find the word W. A good word will be an empty word. An empty word belongs to R. Since we have 0 star, and in 0 star we have epsilon. So epsilon definitely belongs to 0 star. and it belongs to R. But epsilon doesn't belong to the second expression, since the second expression has at least one letter 0 or 1 in prefix, and then it has a concatenation of suffix that has some structure. But we definitely have at least one letter in S. Therefore, W, an empty word, doesn't belong to LS. And here we actually proved that two regular expressions are not equivalent. Okay, our next topic, equivalence of regular expression and finito automaton. It doesn't matter which finito automaton, non-deterministic or deterministic. Regular expressions and finito automata are equivalent terms because we are talking about languages. We are talking about describing languages or accepting languages. So our basic theorem will be a language is regular if and only if some regular expression describes it. This theorem has two directions, if and only if, so we will prove each direction separately. Before we start our proof, I would like to remind you equivalences that we have so far. For each DFA, we have an equivalent NFA. For each DFA describes some regular language, or each DFA has a regular language. Now we will prove that a regular language is equivalent to regular expression, and we will prove that regular expressions equivalent to some NFA. Okay, so let's start to convert a regular expression into finito automaton. Our claim is if a language is described by a regular expression, then it is regular. To prove that the language is regular, we used finito automaton. So the proof idea will be, we will start with some regular expression R, and we will start building NFA by transforming the regular expression R into non-deterministic finito automaton A, such that the language of A will be equal to the language of R. And we will have some well-defined algorithm how we transfer a regular expression to non-deterministic finito automaton. So basically, we will convert a regular expression to non-deterministic finito automaton, and we know that for non-deterministic finito automaton, we have a regular language. Okay, the algorithm will be the following one. We will start building an automaton with two states, Q starting state and P accepting state. And on the error, we will write on the H, we will write the whole regular expression. So we have H labeled with R between Q and P. And currently, we are allowed to use the whole regular expression, not single words, as a notation, for labeling the edges of the automaton. We will transfer a regular expression to non-deterministic finite automaton A by applying the following rules in order they are written until we have edges in the automaton labeled only with single letter sigma or with an empty word epsilon. Okay, let's define. If an edge is labeled with an empty set, phi, and we have transition from I to j labeled with phi, we delete this edge. So in our automaton, we will have the state I, we will have the state j, but we won't have any label between any transition between I and j. The next step, for all the expressions r plus s, we will draw two edges from I to J, the first one with R, the second one with S. If you have concatenation regular expression, R concatenation S, written between I and J, we will add additional state between I and J, and we will write or we will transfer the following operation. We will move from I on R to this new state, and we will continue from this new state with S to J. So we now have R on the edge between I and new state, and S written on the edge between new state and J. The next operation, let's define what we will do for star operation. If we have R star written between I and J, we will do the following transition. Once again, we will add additional state between I and J. We will have a self loop with R to this new state, and we will move from I to new start with epsilon transition, and we will continue to move with from this new state to J with epsilon transition, since R star means also an empty word. So we definitely have a possibility to move from I to J with empty word only. So once again, we continue to apply steps 1 till 4 of the algorithm until we have a non-deterministic finite automaton where on each stage, each edge, we have only a single letter of the alphabet or epsilon transition. Let's do an example. Okay? We are given a regular expression B start or A concatenation B, and we are asked to construct an NFA for this regular expression. So we start with applying the algorithm. We draw two states, the beginning state, initial state, we will call it S, and the final state, we will call it F, and we write the whole regular expression on the edge between S and F. Now we continue with the algorithm and we apply all the stages. So we will use, since we don't have an empty word, we don't use rule number 1. We will use rule number 2, and we will redraw two edges, and on the first edge we will write B plus, B star, and at the second edge we will write A concatenation B, and we will delete the previous edge and the labeling that it had. So now we have a new automaton with two transitions from S to F. Now we will apply rule number 3, and we will divide the concatenation between A and B. We will add a new state between A and B, and we will have an edge from S to new state with A, and from new state to F with B. The last step, we have still a star operation, so we will use rule number 4, and instead of B star, we will once again draw an additional state. We will move from S with epsilon transitions to this state. We will have self loop with B's to imitate B star operation, and we will continue from this new step with epsilon transition to F. The resulting automaton is an NFA that is equivalent to the regular expression that we had. So the final NFA can be seen here, and we have, please pay attention, we have two additional examples that we will solve during our recitation hours. Okay, let's continue. Next, we will convert finite automaton to regular expression. Okay, we have the following claim. If a language is regular, then it can be described by a regular expression. This time, we will take some deterministic finite state automaton M and we will transfer it to regular expression, such that the language of a regular expression R will be equal to the language of the automaton M. Once again, I would like to remind you that we can take regular language, transfer it or build a DFA for this regular language, and now we will learn how to build regular expression for a DFA. Okay, we will convert regular finite automaton into regular expression the following way. We would like to take our DFA and we would like to deform the DFA into new machine with ages labeled with regular expression. And we want to continue with this automaton until we have only two states, the start state, initial state, and the finish state, and only one age with the regular expression of the automaton written on this age. Before we start our solution, we will transfer the given DFA into generalized NFA. Generalized NFA might have a regular expression as a label, has a single accepting state. We will draw a single accepting state. The start state doesn't have any errors going in, and the final accepting state doesn't has any errors going out. Okay? Additional thing, except for the start and accepting state, one errors goes from every state to every other state, including itself, including a self loop, and in each direction. Okay, so let's convert a given DFA into generalized NFA. We will start with DFA with its 5 tuple, Q, sigma, delta, Q0, and F, and we will create a new start state S, such that we will have a transition, epsilon transition from S to Q0 for of our automaton N. So we have now a new transition with S and epsilon leading to Q0. Next, we would like to create one single accepting state F, and we will draw new edges labeled with epsilon to this new accepting state. So we have an additional state F, and we have transition function delta for each state Q in F with the epsilon transition leading to F. So delta Q epsilon equals F for each state that was in original automaton in set F. The new accepting state will be a new state F that we added to our automaton. Okay, now we will take each pair of states I and j that have more than one edge between them in the same direction and replace them with a single edge labeled with a regular expression. For example, we have here the states rj and we have two labels, two edges labeled with r and labeled with s. We will draw only one label and we will write regular expression r o s. If we have two states with no edge between them, we will add two edges with empty set written on them. An edge from I to j with an empty set and from j to I with an empty set. We didn't finish yet the algorithm, but let's see how the transition from DFAs to generalized NFA works. We are giving a deterministic finite state automaton, and our task is to build a generalized NFA. We will start with adding the new start state and the new final state with epsilon transition leading from S to Q0 and from previous accepting state Q1 to F. Now we will add additional edges with epsilon with an empty set where we didn't have any labels, and we will replace some edges, double edges, with regular expression written on it. So when we had A, comma B, the meaning of comma was that we had actually two edges. For example, in Q1, we had an edge with A and an edge with B. Now it can be written as a regular expression A plus B, and we had the same at Q2. The next step is to convert generalized NFA to regular expression. We will use old ij notation to label age ij of the current GNFA. We will construct a sequence of new GNFAs by eliminating one state at a time until we reach only two states, except a start state and an accepting state. The order of elimination can be chosen by arbitrarily, it doesn't matter. So we will construct a new machine with less state, with less state, with less state until we reach a machine with only two states, S and F, and the regular expression written on the edge. When we eliminate some state K, we have to write the correct notation and to update our labels. So we had a transition from I to J, old ij, and now we want to delete the K state. And if we want to delete the K state, now we will have additional transition from I to J. And additional transition from I to J will have the following notation. Old IK, old KK star since we had a loop, and all KJ. So please see if I eliminate, I have the following age. Old IJ as we had, plus this additional new age, old IK, the self loop old KK star, and old KJ. So we will define new ij as old ij plus old ik, old kk star, old kj. Please pay attention. When you delete some node k, you have to update all the couple of states ij going through k. After eliminations of k state, we have a new machine without the k state. We updated some edges to the new ij label, and we continue with elimination of nodes of states until we have only two states, S and F. So the algorithm terminates when we have only two states, the initial state S and the final state F, and we have only one edge with regular expression new SF representing the language of the original automaton. Let's do an example. So we have generalized FA and we want to compute the regular expression of this automaton. So we will use the elimination algorithm, and first we will eliminate the state Q2. When we eliminate the state Q2, we don't have passes through Q2 to other states. Therefore, we don't need to do anything. The deletion of Q2 can be without adding any new information to the edges of the automaton that we have. Next, we will eliminate Q0. We have a transition from S to Q1 going through Q0. So we will have to write a new transition function. We will have to take into account the transition between S and Q0, the loop in Q0 that we currently don't have, and the edge with A from Q0 to Q1. So we add a new edge from S to Q1 and written with empty set. And now we will add to this edge our current transformation, old SQ0, which is epsilon, old Q0, Q0 star, which is empty set star, which will give us epsilon, and we have old Q0, Q1, which is A. So we have an empty set plus epsilon, empty set star A. Empty set star, I remind you, is epsilon. So we have epsilon, concatenation A. So we have phi plus A, and this is equals to A. So we have a new automaton with only A written on it. Now we will eliminate the last state, which is Q1. Once again, we will do the same thing that we did before. We will add an empty set transition from S to F, and we will write old SF expression and new SF expression. Old SF, once again, is an edge with an empty set. Old SQ1 is A. Old Q1 A plus B star, and all Q1F is epsilon. So we have A, the loop of A or B, and epsilon. So phi plus something, phi doesn't matter, plus something matters. A concatenation A plus B star concatenation with epsilon can be rewritten as A concatenation with A plus B star. Therefore, the resulting regular expression that represents the given DFA is A concatenation A plus B star. Additional examples that we will do during practical exercises. We will be giving the following DFA, and we will have to write a regular expression for this DFA, but we will use the algorithm. Even if you see the regular expression, we will use the algorithm during our practice exercise. The next example will be this automaton, and once again, we will be asked to give a regular expression for the language of the automaton, and once again, we will use the algorithm. That's it. We finished Unit 4. Once again, regular expressions are used a lot in programming languages to write a validation. They're used a lot in artificial intelligence for understanding the natural language and performing some text transformation. As regular expressions also used in compilation techniques. Therefore, it was a very important unit. Thank you very much for listening. See you during our Zoom practice meeting.